Resistors apply resistance for the flow of electric charges. How is the variation of the graphical representation when you compare I as well as V? Semiconductors, sometimes it acts as a conductor or sometimes it acts as an insulators. When the number of free electrons increases, the flow of current is more than that of the resistance which is present over there. Hello everyone, I am Brunda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 3 of chapter 3, and chapter name is Current Electricity. So in today's class, we are going to discuss more about the resistors, the resistance. Resistance, it is the opposing power which a circuit will give. So there is a resistance which is offered by certain component called as resistors. Resistors apply resistance for the flow of electric charges. So for example now, let us deal with limitations of Ohm's law. Because in a previous session, we had studied about the Ohm's law and how did you get the resistance formula for Ohm's law. So now what are the conditions which doesn't support or supports Ohm's law? So that comes under limitations of Ohm's law. See here, in case of conductors, Ohm's law is told to hold good. Ohm's law holds good for metallic conductors because the potential and the current graph is linear. That means we have a graph over here, that is current in x-axis, potential which goes in y-axis. So now it is told that VI graph is linear in case of conductors. That is why it is told that, so this is linearity condition. That is why it is told that the Ohm's law holds good for the metallic conductors because of its linear variation. That is, as the current increases, the potential also increases. That is what it is given over here. Now coming to the semiconductors and ionic conductors, call it as electrolytes, where exactly the ions are the one which acts as a conductor as well as plasma. Here the proportionality doesn't hold good. Why the proportionality doesn't hold good? Because the current in x-axis and potential in y-axis, this graphical representation shows that the curve is not linear, but it is a kind of a parabola. So for this, proportionality doesn't hold good, wherein this VI graph is not linear. So this is only for the semiconductors. The devices which is used under this is known as non-ohmic devices, and the devices which we use under this condition is known as ohmic devices. So that is the difference between ohmic as well as non-ohmic devices. In ohmic devices, the proportionality of current as well as potential holds good because it shows the linear condition. In non-ohmic devices, the Ohm's law doesn't hold good and it doesn't show any linear variation. It shows just the increase over there, that is increase in the curve, but no linear variation. So now example for this you can give as germanium, silicon, all these are the examples of the semiconductors. So this is one of the limitation when you just bothered about the semiconductor. Now let us look into semiconductor diodes. So here we have got diodes. Example, we have taken Zener diode, PN junction diode, LEDs and all. So here now, how is the variation of the graphical representation when you compare I as well as V? So in such cases, that is in case of semiconductor diode, when you draw a graphical representation as potential difference versus current, it has got different values for the same current. So that is all about this semiconductor diode. So now we are moving on to resistivity of various materials. We have to get deep inside the resistance. So what is meant by resistance over here? Resistance is the one which opposes the flow of charges. So in order to check what are the materials which give certain resistance, we have to see which materials possess more number of resistance to the flow of charges, which material possess least number of resistance to the flow of charges, and all we will have to check. So we have considered metals, semiconductors and insulators. So metals are the one which conducts electricity, that is highly conductive nature is present in case of metals. Semiconductors, sometimes it acts as a conductor or sometimes it acts as a insulators. Insulators are the one which will never conduct electricity. Okay, that is completely insulated, so there is no flow of charges within it. So here it is, the one which conducts electricity. Semiconductor is the one which either acts as a conductors or acts as a insulators. What is insulators? The one which never conducts electricity. You can give the example of a wire which is covered with that insulator. You have green color wires, black color wires, red color, yellow color. There are too many colored wires, correct? So those colored wires, that is external color is there, no? That is nothing but the insulator. That is, it will never allow any of the charges which is present within that wire, a copper wire or wire which is present, it will never allow the charges to flow out of it. Okay, so that is known as insulators. So this image corresponds to the resistor image. Okay, so this is a resistor. So you might question, so what is this? If this is a resistor, this is known as a carbon resistor. Okay, it's very small and it has got certain values. So that value, that is like how much of resistance value we are supposed to take so that our circuit connection will be made. So suppose you have seen in your laboratories, you will have components with certain resistance. And how is that? How to find out value? By having this cylindrical kind of an object. Okay, it is very tiny and very cylindrical kind of an object, wherein by looking at it, many of us give the values of certain resistance, because this is having certain value, this resistor has certain value, this also has certain value. Each and every resistor differs in its value. How do you give that? Let us see. Color coding. There is a term called as color coding, means having a color you will give the values. So how do you keep those color coding values in your mind? In order to give the values, you will have to know which color is having certain value. For that, we have a shortcut, and that shortcut is nothing but B.B. Roy of Great Britain have a very good wife wearing gold silver. So you might question, what exactly there lies in this B.B. Roy sentence? It is nothing but B.B. Roy, that means black and brown. Black, brown. Roy means R for red, O for orange, Y for yellow. And you have G for green. B.B. Roy of Great Britain. Britain is by word B. So B means it is blue. So we have B.B. Roy of Great Britain is over. Had a very, V for it is violet, G for it is grey. First it is green and then it is grey. Had a very good wife. So W for it is white. Wearing gold is one color, silver is one color. So what is the shortcut we use? B.B. Roy had a very good wife wearing gold, silver. So that is all about your color coding. Now let us give the value. That is, now let us substitute the value of this color coding. So we have color coding of resistors. We are talking only about resistors. So in this chapter, our concentration is only on the resistors now. So now here we have got BB, ROY, Roy of Great G for green, Britain, B for blue, had a very good wife. Had a is left out, very violet, good is grey, wearing, had a very good wife. Wife for it is white, who wears, that is wearing gold and silver. Okay, so this is the color coding nature. So now let us just make columns. So we have 3 columns over here. So this corresponds the numbers, that is the values, the first 2 values. This table, that is this column gives the multipliers, and this gives the tolerance. So we have color coding in this way: black, brown, red, orange, yellow, green, blue, violet, grey, white and gold, silver. So now we are supposed to substitute the values. So we start from the whole number, that is 0. Black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8, white is 9, wherein we leave these 2 lines of gold and silver. Gold is a separate color, silver is a separate color. Let us give the tolerance to it because it has got certain tolerance. Okay. Now, coming to the multipliers. How do you give the multipliers now? So, everything is to the power. That is into 10 to the power of something, into 10, into 10, into 10, into 10. Everything you are supposed to fill it up with the into 10. So now we have multipliers as into 10. We'll have to substitute it with the powers. We have to give the powers to each of the multipliers. So we have black is 0, so to the power of 0, or it can also be called as 1. Because anything to the power of 0 has got the value unity. Next, brown is 1, so to the power of 1, red 2, this is 3, 4, 5, 6, 7, 8 and 9. Now, coming to the tolerance, we are only checking on to the tolerance of gold and silver, which is written as plus or minus 5% for gold and plus or minus 10% for silver. So now, here comes the color coding of the resistor. Having these values in your mind, you're supposed to give the values for the resistor. So there is a small exercise for each one of you. I want you people to look at this color coding and give me the answer for the resistor's value. What is the value of the resistance? Before checking the value of resistance, we make sure that either gold or silver will lie towards the right hand side so that we check the color coding from this way. From left to right is the checking of the color coding. So now we have yellow, violet, red and gold. So what is the value of yellow, violet, red? So these two are the values from first column, third value is from the second column and last value is from the third column. That is the tolerance. Red will be the multipliers. The rest of the two is from the numbers column. So now let us take, first was your yellow, violet. So yellow is 4, violet is 7. So just write the same, 4 and 7. Now we are checking for the red in the second column. Red color in the second column into 10 to the power of 2. So you can write into 10 to the power of 2. Okay, and gold color is nothing but the tolerance. For gold, it is plus or minus 5%. So I can write plus or minus 5% is the tolerance. How can you, so this is the value of this resistance. So how can you rewrite this value in terms of ohm? It can be easily written as, that is, just add a point to it, so it becomes plus 1, so it becomes 4.7. 10 to the power of 3 is nothing but kilo, so you can just write it as kilo, and resistor is given in terms of ohm. So 4.7 kilo ohm, and the tolerance is plus or minus 5%. So this is one of the resistor's value. Coming to the second one, it is red, and gold. So for this we have, coming to the previous table, what is red? It is 2. You have all in reds. All 3 values in reds, and the last value is in gold. So 2 into 10 to the power of 2. Okay. So for this red, it is 2. Again for this red, it is 2. Again for this red, it is into 10 to the power of 2. So first 2 values have to be seen in this one. That is, the third value should be seen in multipliers. Fourth value should be seen in the tolerance section. Okay. So now into 10 to the power of 2, and gold is the tolerance of plus or minus 5%. And adding this 1 point here, what happens? 2.2, it becomes plus 1. So into 10 to the power of 3 is nothing but kilo. So it becomes kilo ohms. Tolerance is plus or minus 5%. So this is how you measure the resistance of this resistors. Okay. So these are the values. So coming to the third resistor, how do you give the value for these resistors? It is brown, green and red. So brown and green has to be seen in the first column, red has to be seen in the second column, and gold in the third column. So gold in the third column, we already know it is plus or minus 5%. Coming to brown. So what is brown in first column? It is 1. So I can just write 1. Again the second one, that is green. Where are we supposed to see green? In which column? It should be in the second column itself. So what is green? Green is 5. So in going back again, we have 1 and 5. What is red? Red is into 10 to the power of 2. So into 10 to the power of 2, and gold is plus or minus 5% tolerance. So 15 into 10 to the power of 2, wherein just add 1 point over here. So it becomes plus 1. You get 1.5. This becomes kilo, and ohm is the SI unit of resistance, and you have the tolerance over here. So this will be the answer for the third resistor's value. And last we have, I want students, you also to write and learn this. That is, you will have to observe the color coding, give the color coding and work along with me in this session. So here we have yellow, violet and black with gold. Yellow, violet, black and gold. So what is the color coding for yellow? What is the color yellow resembles? That is, in the first column, yellow is nothing but, once again, it is 4. So I'll write it as 4. And the first column itself, what is the value of violet? It is 7. So we have 7. And what is the value of black in the second column? It is 10 to the power of 0, or it can also be called as 1. So you have into 10 to the power of 0, and tolerance is plus or minus 5%. So how will you give the resistance to this? It is 47 ohms, and plus or minus 5% is the tolerance of the resistor. So 47 ohm is the value for the third resistor. So that is all about here, the value. How do you give the value for each of the resistor? Only by looking at the resistor, so that you will get to know which component, that is which of the resistors which is having certain value to be used in certain laboratory experiments. Clear? So now it is all about the resistor. How many types of resistors are there? There are two types of resistor. One is wire bound resistor, another one is carbon resistor. So this is the wire bound resistor, this image, and carbon resistor is the one now recently we gave the values. No, these are nothing but the carbon resistor. So wire bound resistor are made up of manganese, constantan or nichrome, wherein the carbon bound resistors are having a high range of resistance. So that is all about the resistors, which are of two types. So let us check how does the resistance depends upon temperature. So this is one of the most important which will be asked in your boards, that is temperature depends of the resistivity dependence, that is temperature dependence of the resistivity in case of metals, alloys, semiconductors. Clear? We know that the electrical resistivity is given as R is equal to rho into L divided by A. That means resistance is directly proportional to length of the conductor and inversely proportional to area of the conductor. Now suppose you're taking metals. Okay, suppose you're considering metals, then how does the resistivity varies with temperature? So you have graphical representation wherein you're measuring the resistivity with temperature. We have the graphical representation in this way. What does this mean? This means to say that this is the curve which is given by copper metal. So remember, copper graphical representation when we compare the resistivity and temperature is this picture. So you will have to know how the copper's resistivity varies with temperature. That is, the resistivity of copper increases when there is increase in temperature. So resistivity increases when increase in temperature in case of metals such as copper. Suppose you consider the alloys. The graphical representation for an alloy is said to be, this is the graphical representation x and y axis. It doesn't start from 0, but it starts from certain number which goes linearly like this. So this is the graphical representation of alloys and this is the graphical representation for the metals. Now coming on to the semiconductors. In case of semiconductors, how exactly the resistivity act? So, in case of semiconductors, the resistivity is given as, this is x-axis, y-axis, resistivity and temperature. It is as the temperature increases, the resistivity decreases. This is in case of the semiconductors. So, in case of metals, as the temperature increases, resistance increases. But in case of semiconductors, as the temperature increases, the resistance decreases. That means increase in temperature increases number of free electrons. When the number of free electrons increases, the flow of current is more than that of the resistance which is present over there. That means when the temperature increases, the resistivity of the material starts decreasing. Clear? So that is all about the temperature dependence of the resistivity. Suppose if T is 0, that is very less temperature, T is 0, then your resistance tends to be infinity. When your temperature is completely nil, resistance is reached up to infinity. More number of resistances applied across the circuit. So that is all about your temperature dependence of the resistivity. So in today's class, we have studied much about the resistance, that is limitations of Ohm's law and how exactly the resistivity is considered and what are the resistors we use, that is wire bound and carbon resistors, out of which carbon resistors are having high range resistance, and how to identify the values of resistance in the resistor by using the color coding. That's all about the resistors. Let us all meet in the next class with the upcoming session of the same chapter, chapter 3, having more and more knowledge about the resistor. Let us play with the resistor. Until then, have a good day. Thank you.